Hey PKL class, we're going to start with our notes for section 3.2, and we're going to study two theorems, Rolle's theorem and the mean value theorem. And I'm saying two theorems, but they are basically the same idea. The mean value theorem would encapsulate also Rolle's theorem. Rolle's theorem would be just one specific case of the mean value theorem. So we'll start with Rolle's theorem. And what that one states, well, actually, they're going to introduce it with just a little bit of an example here. And I think from this, we can kind of see the main point of what it states, okay? And it is an existence theorem. It's going to state that there exists some certain slopes involved here. So in the first activity, it says to place 2 points anywhere on the coordinate plane that have the same y values. So with what we have right here, so we're starting somewhere over here at 0, and we're ending at 1, 2, 3, 4, about 5. So I'm just going to put one somewhere on the x-coordinate of 0 and the same y-coordinate at the x-coordinate of 5, about right here. And then it says what we should do is connect the 2 points with a continuous function that is also differentiable. So continuous meaning, we can't pick our pen up or our pencil up. We just have to connect them somehow. Differentiable meaning no sharp corners, no vertical tangent lines in there. You can have a vertical asymptote, and I guess that would make it discontinuous, but we couldn't have like a cusp or anything like that in there. Okay, so most continuous differentiable functions are a lot of times they're just like polynomial functions. So I'm just going to draw something that might look like that wasn't very good, but we'll pretend that looks pretty continuous and smooth. But okay, so if we have something that looks like that, right? Okay, so we've done this. It says conclusion is that there must be at least one point on your function where you can draw a tangent line that is horizontal, i.e. the slope is 0. Okay, and with what I did, and I could have done, more up and down waves in there, but the way I drew it, it looks like there are two positions or x-coordinates that would yield a horizontal tangent line. Because I can see there's a min, a relative, actually it's an absolute min, but whatever. There's a min here and a max here, which is going to give us that horizontal tangent line. Now, according to Rolle's theorem, again, which is a specific form of the mean value theorem, as long as these y-coordinates are the same and that we have a continuous and differentiable function, there is guaranteed to be at least one spot on that in that interval, one x-coordinate at least, where you have a horizontal tangent line. It's got to be true because, the slope, if they have the same y-coordinates, the average slope is going to be 0. So somewhere in here, we've got to have a horizontal tangent line or an instantaneous slope of 0. Okay, so that activity basically models an important concept called Rolle's theorem. Okay, now specifically, here's what we need for Rolle's theorem to apply, and then what it says once it does apply. So it says let f be a function that's continuous on the closed interval, whatever those in this case, it looks like we were 0 to 5 is what we had on the graph. But on the closed interval, it has to be continuous. You have closed dots on the ends, and it's continuous all the way through. And then differentiable on the open interval. They make that distinction just because you can't take the derivative at the endpoints of your interval. So they say on the open interval, it's differentiable. And then here's the key part, that these are y-coordinates, right? F of A and F of B, meaning, the y-coordinate at your starting point of your interval, the y-coordinate at the ending point of your interval are equal to each other. It says if that all holds true, then there is at least one number c. Now they use c just meaning some x-coordinate in that interval. Such that f prime of c equals 0. And so what does that mean? F prime of c meaning the derivative at c, which is the slope of your tangent line, is equal to 0. So we see in the way I drew it, there were two of those. There were two c values where we had it equal to 0. Okay, so that's Rolle's theorem. All right, so example 1, illustrating Rolle's. So determine if Rolle's theorem applies, and we've got a polynomial function, just the 4th degree, on the interval from -2 to 2. State thoroughly the reasons why or why not the theorem applies. If the theorem does apply, find the value of c guaranteed by the theorem. Confirm your results by graphing the function in the coordinate to the right. Okay. All right. Looks like we have a typo there, but that's okay. So the first thing, like if you were doing this on the AP exam, you don't really, if you can just look at this equation, you can say this is a continuous function, and your knowledge of polynomial functions isn't, it's enough just to say, yes, this is continuous. The main thing is if it's not continuous, like if it was a rational function and you were dividing by x, or you're dividing by something with an x in it, then you'd say, well, it's not continuous because the function is a vertical asymptote at whatever. Or if it were, let's say, an absolute value function at a sharp corner, then we have to say, well, it's not differentiable because it has a sharp corner in there, okay? So those are some things to look out for, and we'll see those later. But this is just a polynomial. Polynomials, we sometimes call those well-behaved functions. They're smooth curves, they're continuous, no things to worry about there. So in this one, we're going to say, okay, so f of x is continuous. Is what we want to say specifically. F of x is continuous, and we want to say where it's continuous. Since we're talking about this, it's continuous on the closed, let me say the word on there. It's continuous on the, and use your brackets to imply closed interval from -2 to +2. And again, because it's a polynomial, we can just say we know it's differentiable, it's well behaved, it doesn't have any issues with it. So we can say and differentiable. We're going to say on the open interval, so we're just going to use the parentheses for that. Okay, and then what we need, the other thing we need to determine if Rolle's theorem applies is that this piece here, that f of a is equal to f of b. So they have to have the same y coordinates at -2 and +2. So let's check that out. So if I were to take f of -2 and f of +2, if I were plugging those in, this is going to be 16 minus 8, whether it's positive or -2, because we're taking to the 4th power and to the 2nd power. You're going to have 8 for both of those, okay? Okay, so it's differentiable. And now we can say f of 2 is equal to f of -2. F of -2 equals f of 2. And therefore, I'm going to use these 3 dots that mean therefore when you come to your conclusion. Rolle's theorem applies. Okay, now, so we've stated that it does apply. Now we need to find those values where, we're going to have those horizontal tangent lines. Okay, so somewhere in there, we're going to have at least one horizontal tangent line, because we know that if they have the same y coordinates, f of a and f of b, then there's a, that basically the average slope is horizontal there. So somewhere in there on your curve, there's got to be some, instantaneous rates of change, or horizontal tangent lines where there's going to be a min or a max on the function. Okay, so how do we find those? We need to take the derivative. So we're going to take f prime, and that's going to give us 4x to the third, 4x to the third minus 4x, and then we need to set that equal to 0 so that we can figure out where that happens. And so when we set that equal to 0, I would solve this by factoring out of 4x, and that would leave me with x squared minus 1, and this is going to factor a little more into x plus 1 and x minus 1, and so my solutions are going to be, for this piece, set 4x equal to 0, I get 0, and set x plus 1 equal to 0, I get -1, and then +1. Okay, so I'm going to have, these are my values where I would have those horizontal tangent lines. So if the theorem applies, which we determined that it did, find the value of c, or it should say value or values guaranteed by the theorem. We have 3 values. Now it did say to graph it to confirm your results. So if we did take just a take a look at this graph, so I put it into the calculator, and if we look at the graph, we can see, okay, yep, there's a horizontal tangent line there, one here, and one here, right? So, and that appears to be exactly what we found. -1, 0, +1 for x coordinates, right? So if I were graphing this, let me look again here. Okay, so we have origin. So we got a point here, 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 and then it does something like this for a graph, right? So we've got horizontal tangent lines at those values, okay? And at -2, we had a +8. I should have probably done that correctly. So up here, we had that dot, and at +2, we were up at, if I counted that right, 1, 2, 3, 4, 5. It should have been up one more. Sorry, I should have been up there. And then this one as well, +2, +8, but it's getting up bit. Okay. So that's the idea. All right, so what we've done is we showed that the Rolle's theorem did apply continuous on the closed interval, differentiable on the open interval, and that f of a was equal to f of b. All right, so all those things were true, meaning we had to have at least one horizontal tangent line. As it turned out, we had 3 in that interval. Okay. All right, so the next theorem, which is closely related, and this is just basically a more generalized version of Rolle's theorem. So instead of just saying that we're going to set that, that derivative equal to 0, meaning that slope has to be 0, this is going to basically say our slope has to equal whatever the average rate of change is on that closed interval. Okay, now the beginning of this is exactly the same. If f is continuous on the closed interval from a to b and differentiable in the open interval, then there exists, again it's an existence theorem, there exists a c in that interval such that instead of f prime of c equals 0, f prime of c equals whatever, so now the y coordinates don't have to be the same. They're saying, okay, whatever, basically whatever this slope is between these points, somewhere in here there's going to be an instantaneous rate of change that matches the slope. Okay, so let's run through this activity here real quick together, and maybe this will help things out. So it says in the figure to the right, label the indicated ordered pairs. So what we would do, since they say a and b, we're going to say, okay, well this is a, this is a, and the y coordinate we'd say f of a, and then this is b, so the y coordinate is f of b. Okay, so that's how we would state those ordered pairs. And then it says label a segment whose length is f of b minus f of a. Well, that's the difference of the the y coordinate source. That segment would be, we're going to kind of make a triangle out of this, and it would be this segment right here, f of b minus f of a. The difference of the y coordinates would be that vertical leg of our triangle. And then a segment that's b minus a would be this length right here, b minus a would be there. Okay, so the quotient is the slope, right? The quotient, it's the difference quotient. That's your slope formula. This would just be the slope of the segment that's joining the 2 points that we labeled there, which is a and f of a, and then b and f of b. Drawing this segment, well, that segment is right. Let me try this thing here. It's this one right here, right? That's what we're talking about right there. Okay. And it says f prime of c gives the slope, right? We know that derivative gives the slope of the line that's tangent to the curve, so tangent, at that point c, and then whatever, c f of c. Okay. So f prime of c means, it's the slope of the tangent line at the point c f of c. Okay. All right. It says on the graph above, locate the c value that's guaranteed by the mean value theorem and draw a line tangent to the curve at x equals c. So this is we're kind of eyeballing this just a little bit. But what we're looking for is, okay, so this is our average, this is our, this expression right here. It's kind of our average rate of change on that interval, this slope here. So I'm kind of looking at where does it appear that maybe my slope is, my instantaneous slope matches. It's kind of here in the middle, I think, as we're going. We're kind of flat here, but now it's getting more steep, more steep. Yeah, it probably matches it right where the corner of my little square is touching right here, I would say. Because now it gets steeper than the line here, if you kind of visualize that. This is steeper than what this line is. But I would say right here somewhere, we're going to have that instantaneous rate of change or slope of our tangent line that matches our average rate of change. I'm going to change this color here. Okay. All right. And so, like I said, I think it's going to be, I don't know, about right here. And it's, if I would draw in that tangent line, it's going to look something like that, I would say. Okay. All right. And it says on the graph above, okay, we drew that. The 2 lines drawn on the graph above are what to each other? Geometrically speaking, they're parallel, right? If they have the same slope, so they're parallel to each other. So parallel. Thus, the conclusion of the mean value theorem can be restated as follows. There will be 2 parallel lines, okay? One through the point, and that was, the a, f of a, and then b, f of b, and the other tangent to the curve at the point c, f of c. C being that x coordinate, and I didn't really label it here, but it would be, right here. That would be C and f of c, but so C would be approximately in here, and then the y coordinate we'd call f of c on that point. Okay. All right. Let's see what we got left here. Yeah, a few more. All right, so example 2 says illustrating the mean value theorem. So determine if the mean value theorem applies to this function 3 minus 5 over x. Now, when we look at this, we got to be thinking, oh, I better be careful with this because it's a rational function. That means that there is a discontinuity in there because there's going to be a vertical asymptote somewhere. Now, so that may disqualify us from using this mean value theorem, but we got to be thinking about the interval that we're working on as well. So we're going to see if the mean value theorem applies to this function on the interval from 1 to 5. State thoroughly the reasons why or why not the theorem applies. If the theorem does apply, find the value of c guaranteed by the theorem. Visually, what is the mean value theorem trying to find? And then we should draw it in kind of like what we did in that other example. Okay, so first of all, it appears to be a continuous function. Now, where would a discontinuity occur here? What would we plug in for x to make this undefined? And hopefully you can see, we'd have to put a 0 in there. That's where, when you have a rational function, whatever makes the denominator 0 is where we have our discontinuity. Now, 0 happens to not be in this interval that we're discussing. So in this case, in the interval from 1 to 5, any other point you put in there between 1 or any other x coordinate that goes in here does not yield any discontinuities. It's all good. So that's what we're looking at. We're just looking from here, to 5. So basically, the only part of the curve we're looking at is this part of the curve right here. Okay, continuous, differentiable. There's no sharp corners. Okay, so I think we can say the mean value theorem does apply here. Okay, so let's state that just that f of x is continuous. F of x is continuous on the closed interval. I should have said on 1, 5. And differentiable on that open interval. So just use parentheses there. Okay. Therefore MVT, and we can abbreviate that. It's well known that MVT means mean value theorem in calculus. Okay, so MVT does apply, more like a U. MVT applies. Okay. All right, so now what we want to do, we have to find, basically what we need to do here is find this point, and then we need to find the slope, right? We need to find the slope of the line that connects those two, okay? So we want to find f of 1 and f of 5. So let's find those values. If I plug those in, I'm going to get f of 1 is -2, and f of 5 is +2, and then I want to do the slope, so f prime of my whatever that c value is going to be. We want to set that equal to f of 5 minus f of 1, so a difference of the y coordinates over 5 minus 1. Okay, and so that f prime of c is going to equal, that would be, so negative, or 2 minus -2 is going to be a 4 on top, and then I'm going to get a 4 on the bottom. That's going to give me a 1. Okay, so my actual derivative, so f prime of x, if I were taking the derivative of this guy, the 3 disappears. The derivative of the -5 over x is just going to be, what I think of there, I'd probably rewrite f of x maybe, let me rewrite this before I just jump into what the derivative is. I'd probably rewrite this, f of x would be 3 minus 5x to the -1, because that's going to allow me to just use that power rule for doing derivatives. And so the 3 disappears, so f prime of x would just be positive 5x to the -2, or just 5 over x squared, right? And so now what I want to do is I want to set, that's my f prime of x right now, right? And so I'm going to set the, and I've got f prime of c is equal to 1, so I'm going to set 1 equal to the 5 over x squared. Okay, so I'm going to set that equal to 1 and solve for x squared. Well, I'd multiply x squared out of the denominator, so that means I would have 5 equals x squared, And so that means I'm going to get square root of 5, which would be, technically you'd get plus or minus the square root of 5, but since we're only working in this interval, I really only need to state positive square root of 5. Okay, so there's the c value, or you could say c equals square root of 5 for that one. Okay, and so square root of 5 is about what? It's about 2 point something. So if I took square root of 5, 2.23, okay. So at about 2.23 on the curve, if we could estimate where that is, 2.2-ish, okay. So maybe like right in here, if I were to kind of try to draw a tangent line there, that looks like that's about right. It looks like it matches the slope of the red line I did that connected the endpoints. Okay, so we showed that it mean value theorem applied, and then we found the slope, the average, rate of change using the endpoints and their y coordinates on the actual curve. Got a slope of 1, and then we take the derivative of our function, and we got 5 over x squared. Set that equal to the slope and say, where's the x value on this curve where I get that value of 1, where I get that slope of 1, right? And so that occurred at the square root of 5. Okay, and that's what we're looking for, is that x coordinate where we get that slope that's equal to the average rate of change. So for this video, I'm going to stop right there, and we'll continue up with the rest of the notes on the next.